Here we go. It is January 16th. We're looking at section 5.2. We have a quiz next class on Tuesday on what we did last time and what we're doing today. I really just kind of want to get this wrapped up before midterms. I didn't want to quiz you on the midterm exam review day. So next class, we will go over homework on this stuff and then do a quiz on these first two sections. We're going to look at integration with the natural logarithm. Integration with the natural logarithm. Very good. Okay, very good. Integration with the natural logarithm. What we are not going to do is this problem. We're not going to integrate the natural log of x dx, because that means knowing what has the natural log of x as its derivative and what has the natural log as the derivative. Yeah, nothing. We don't know anything where natural log is, we know the derivative of the natural log, that's 1 over, we don't know what has natural log as the derivative. What instead we're going to look at is this integral, the integral of 1 over x dx.
So that's just like
so this is asking you what has 1 over x as its derivative. Natural log. Well, actually, last class I showed you two different things that had 1 over x as its derivative. One of them was just the natural log, but technically that was only good when x was positive. Then I gave you a more general one a little bit later with absolute value bars in there. And to make our answer as general as possible, we are going to need absolute value bars in here, which really makes this valid for any x value except for 0, because 1 over x is good anywhere. So I kind of want an antiderivative that is valid everywhere. The integral of 1 over x dx is the natural log of the absolute value of x plus a constant. Before we go on and do some other problems, what I also want you to realize is this rule is sort of a special case of our power rule. I also want to write it like this. If I want to do the integral of x raised to the n dx, in general, this is x to the n plus 1 over n plus 1 plus a constant, our normal power rule, as long as our power is not what? No, we can do 0. Negative 1, you can't do that one. If the power is negative 1, x to the negative 1 is like 1 over x. What's the integral of 1 over x dx? What's the integral of 1 over x dx? Natural log of the absolute value of x plus a constant. This is really a special case of our power rule if the power happens to be negative 1. So when we try to integrate, we're going to use power rule, unless that power happens to be negative 1, and then we're going to get things with natural logs in it. So for our first, hopefully easy example, I want to do the integral of 10 over x dx. The integral of 10 over x dx. Do I need the 10? Or can I move it? Now, move it out front as 10 or as 1/10. I'm not doing u substitution work here. It's truly just a constant that I'm going to move out front. I'm going to make this 10 times the integral of 1 over x dx. Okay, well, what's the integral of 1 over x dx? Of? No. Natural log of the absolute value of x plus a constant, which is fine for the answer. But I actually could do a little bit more. Trey, I would really suggest paying attention to this stuff right now and look at the test later. 10 times the natural log of the absolute value of x plus c, which is fine. I could do something a little different, though. Where could you, now that we're done, forget about calculus, back to pre-calc algebra stuff. By properties of logs, what could I do with the 10? I could turn that into a power. And actually, if I do that, Would I need absolute value bars anymore? No, because x to the 10th is always going to give you something positive. So I could also say my answer is the natural log of x to the 10th plus a constant. Either of those would be okay.
If it was to the ninth,
To the 9th, we would need absolute value bars. Exactly. So I'm going to kind of have to constantly think about, do I need to keep the bars, or is this new operation I applied to it going to get rid of the negative possible issue anyhow? Okay, another one. I'd like to do the integral of 1 over 2x plus 3 dx. What was that? Oh, yes. The integral of 1 over 2x plus 3 dx. Now, today, we should not be thinking about things like product rule, quotient rule, chain rule. We're not doing derivatives. We're doing integrals, and there's really only one big trick that we know for integrals. There's that piece, but we just had a test on this. It was 4.5, that last section. U substitution is our main trick for dealing with some things over here. With that in mind, what could we make U? Let's try it. If I make U 2x plus 3, then its derivative, what's du? 2 dx, which I feel like, yeah, we can make this work. Put what inside? 2. Put what outside? Oh, can we see that or not? It's kind of there. 2 inside, 1/2 outside. And the point is, now we can turn this problem into 1/2 times the integral. Well, that 2 dx thing, that's all included in my du. I can put that up top. And my 2x plus 3, that's my u that's in the bottom. This problem's now the integral of du over u, or I guess you could say 1 over u du. They both mean the same thing. So it's what?
Oh no, I was going to say du.
Yep, du over u or 1 over u du, either way is fine. What's the integral of du over u or 1 over u du? Natural log of the absolute value and all that stuff. We're going to get 1/2 times the natural log of the absolute value of 2x plus 3. That's our definition. Well, sure, but we're trying to integrate like u to the -1. That's our special case of the power rule, because you can't do u to the -1 plus 1 over is not going to work. So this is our new special case when that power is -1. Okay? So we're going to get 1/2 times the natural log of the absolute value of 2x plus 3 plus a constant. I suppose if I wanted to, what else could I do? Yeah, or do a square root. Either one would be okay. I could say natural log of, I guess I have to make sure this thing is positive, so I'm going to keep the bars over there. Yes. We have our rule that says the integral of 1 over x dx is the natural log of the absolute value of x, the opposite of what we did yesterday. Okay, so my power rule now says if I want to integrate any power other than -1, add 1 to the power divided by the new power. If the power is -1, that was our issue that we ran into yesterday. Add 1 to the power, that's okay, 0 for the power. 0, not going to work. What is the integral of x to the -1 or 1 over x dx? The natural log of the absolute value of x. That's why we're not doing the old stuff. We need to use this natural log thing. You okay? Okay, so let's try another. Let's try the integral of 3x squared plus 1 over x cubed plus x dx. And I'd like to see if you can figure out u and du. Yeah, it does. If I change the numerator by a little bit, you wouldn't be able to do this problem.
The plus sign isn't raised.
No, no.
Okay.
Right. Actually, let's do that in a minute. What's u? Yeah, I guess you have a choice of either the top or the bottom when you're trying this, but the top, the derivative of that's not going to show up. We're going to try making it x cubed plus x. Its derivative then? Is that a good thing?
Yes.
Oh, sure it is, because this problem is now just the integral of du over u.
Are we ever gonna get a problem where it's like,
Not yet. Just enjoy this for now. Go finish it. Go integrate your 1 over u du. Natural log of the absolute value of u plus a constant. Natural log of the absolute value. Do I need the absolute value bars here?
no?
I guess my question is this thing always positive? No, it's not. So we need those bars to make sure that thing is going to be positive. Yeah, we do need them here. If the problem inside was like x squared plus 4, would I need the bars? Because that thing, I guess I shouldn't say positive. I guess I should say not negative. But that thing would always be non-negative. Anything with this? Marissa?
For the one I love this, why couldn't you just like assume that it was just the one, like it was just 2x plus 3? Because like,
That's what we did. That's what we assumed. That was what we made our u.
oh,
Our u was 2x plus 3. Its derivative was 2 dx, so everything kind of worked with that. So then I needed my 2 inside and my 1/2 outside to make that u substitution take work. Is your issue with that 1/2?
yeah, like I guess I don't know where, like
So,
I get how you found
it-
the u and du,
it-
but I don't know why it exists. Like, you know what I mean? Like,
Okay, because my du is 2 dx, which means I need inside my problem not just dx, but I need 2 dx. So I had to stick the 2 inside. So I had to cancel it out with my 1/2 outside. Just like the last chapter. Rohit.
Okay.
Trey.
Is 0 negative? No, right? 0 is positive.
Right, which is why I guess I really shouldn't say is the thing inside positive. I really should say is it not negative, which means 0 would be okay. Okay. Next. Let's take a look at this. The integral of the cosecant squared of x over the cotangent of x dx. The integral of the cosecant squared of x over the cotangent of x dx.
Well, this one works over here.
If we're going to do this, what could we make u? Let's try it. If we say u is the cotangent of x, then its derivative is what? Negative cosecant squared x dx, which kind of works. So what do I have to do? Negative in. Is orange going to show up? Kind of. Negative out. Okay. So looks like that whole thing is now du, and I'm getting negative the integral of 1 over u du. Go finish. Du over u is fine. Either way is just fine. I will interchange the two types.
I feel like that makes more sense.
Then do it that way. They both mean the same thing. Integral of 1 over u du is the natural log of the absolute value of u plus a constant. What was u? Cotangent of x. Jill, ask me a question. I know you have one. Should I start from the beginning? That is not super convincing.
I was like, where did the du go? But it just goes away.
Sure, that's the whole point of our u substitution. I'm replacing this whole thing with du, that piece afterwards. Trey.
Do you have to put the negative one at the top? Like, of the cotangent?
So that's kind of what I was always doing in the last unit. Put a 3 inside and a 1/3 outside. I kind of want to see like how the
No,
u
but, like,
sub.
because it's ln, you moved it.
Ah, okay. So this would be okay for an answer. We could also make this the natural log. Actually, natural log of the absolute value of the cotangent of x to the negative 1 plus c. What's cotangent x to the negative 1 or 1 over cotangent x?
So C, no.
tangent. We actually could say this is just the natural log of the absolute value of the tangent of x plus a constant. That would also work.
Will they do that on the?
Probably not. But realize that you can move the numbers into powers and then do some work with that. Okay. I have two more before we make these a little bit different. The integral of 1 over x times the natural log of x dx. The integral of 1 over x times the natural log of x dx. Please stop talking. And he is still talking. Thank you. Okay. We have not done any problems that have had a natural log inside them before. Do you remember what I told you the integral of the natural log was? That's the derivative. Yeah, we're going to learn about it in May. I haven't taught you this yet. What are you saying in the back? Oh, never mind. So what can we do? Okay, making you what? What was that? Okay, so Daphne is saying, how about we make you the natural... I don't know, let's try it. Which you have. Okay, so u is the natural log of x. Please watch. Its derivative. What's the derivative of the natural log of x? 1 over x dx. I guess my question is, do we have 1 over x dx? Oh my goodness. So this is going to become the integral of du over u. Okay, if you were saying u du, that would be the problem like the natural log of x over x dx. I've got the natural log in the bottom. That u has got to go in the bottom. Lily, question? Okay, it's going to look weird when you're done. Natural log of the absolute value of u? Yep. But there was a homework problem with like that in reverse with the derivative. The derivative of the natural log of something. If you have a question, please ask me a question. Okay, we're not talking about buffalo chicken though.
They were.
Okay, we're moving on. So remember what I said about like how I was kind of challenged for time in A block when we did this? I don't want to have to rush at the end. Please don't talk. Questions on that one? I have one more that I want you to try.
So we just ignore it?
Ignore what? What are we ignoring? This was like that homework problem, though, where you had to find the derivative of the natural log of something. It's a natural log inside something.
So is that like we can find the derivative of the smiley face and then we'll do the smiley face and then? Do you need another
Sure.
set of
Yeah,
you know what I'm saying?
I know what you're saying.
No, because the original problem, u was not the natural log of the absolute value of x. U was just what I had in the problem, natural log of x. Okay, one more that you're going to go do on your own. And I need you to stop talking.
So it doesn't really matter what is your u because it's just going to go in the absolute value.
Yes. Sort of. Yes. Try this one. The integral of 1 over the square root of 2x minus 1.
But it's not 1 negative 1.
What's u? What's u? What's u? What's du? So hold on. I can make it work by sticking a 2 inside and a 1/2 outside. And I can turn this into 1/2 times the integral of 1 over the square root of u du, or du over the square root of u. Now, Trey, what were you saying a moment ago?
The exponent is not negative 1.
So am I going to get natural logs from this? The point of me showing you this is really this is The -1 thing is a special case of our power rule. If our power is anything else, we do exactly what you did in that last chapter. There should not be natural logs in here. Just because there's a denominator doesn't mean you're going to get natural logs in your answer. How are you going to do this? I think you should do this as 1/2 times the integral of u to the -1/2 du. The power's not -1, so we're not going to get natural logs. I could have given this to you on the last test. Go finish it off. What I did want people to see is just because there's a denominator does not mean you're always going to get natural logs like every other problem we've seen today. Yes. Yes. So you don't just see denominator and think natural logs. No. See, is the power really -1? And if it's anything else, no, you need to use old things. Oh, that's actually kind of nice. The 1/2 and the 1/2 will cancel. And if you don't see that, this is like 1/2 times 2, so that'll cancel. Just getting the square root of 2x minus 1 plus c. No natural logs. Anything here? There are 3 variations that we need to look at for the rest of the period. Including definite integrals and some trig stuff. But before we do that, we need to go back and do some Algebra 2 review. Once people are done writing. Jill, are you still copying?
I'm good.
Okay, next. Couple. I mean, that's like one of the 4 topics in the class. I'm sorry, not everything is fun in life. Okay. Not right now. Not right now.
What did you eat for breakfast this morning? Okay, no, I actually don't know.
I would like to continue.
We'll continue when you tell us what you have to do.
Again, we do have a quiz on this stuff next time. I'd like to actually finish teaching this stuff, so there won't be things on the quiz I've never taught you. Oh, good. The next method we need to look at goes back to something from Algebra 2. Long division. Here's the deal. And actually, this is going to show up from time to time from here until the end of the year. Anytime we try to integrate a rational function where the degree of the numerator is greater than or equal to the degree of the denominator, we're going to use long division to rewrite it. To integrate a rational function, where the degree of the numerator is greater than or equal to the degree of the denominator. First, use long division to rewrite. And yes, we'll review how long division works. Anytime we're going to integrate a rational function where the degree of the numerator is greater than or equal to the degree of the denominator, we're first going to use long division to rewrite the problem in a better form for us. So I'd like to look at the example of the integral of x squared plus x plus 1 over x plus 1. And I'd think that if you tried your u substitution, u equals x plus 1, du is 1 dx, there's a lot of stuff that wasn't taken care of here. So that's not going to work. Because the degree of the numerator is greater than or equal to the degree of the denominator, I'm going to start by using long division to rewrite the problem in an equivalent form. So I'm going to go and I'm going to divide x plus 1 into x squared plus x plus 1. We divide, we multiply, we subtract, we bring down, we start the thing over. I'm going to do x squared divided by x. What is it? X. I'm going to put an x up top. I divided. I'm going to multiply. X squared plus x. I'm going to add in parentheses so I can subtract. And actually, both of those pieces cancel. That's kind of nice. And the last piece, I can't actually do any more division, which means what is the last piece? The remainder. And the whole point is this answer is the same function as the original function, just written in a different form. That's the whole point of division. We're just rewriting it in a different form. So rather than doing the original problem, I could instead do the integral of x plus 1 over x plus 1 dx. And actually, x is easy. 1 over x plus 1, though, is going to need a u substitution. I really should do this as two separate integrals, because I'm going to handle them each a little differently. I'm going to say this is the integral of x dx plus the integral of 1 over x plus 1 dx, or dx over x plus 1. Either way means the same thing. First one, wait a moment. First one will be easy. We'll deal with that in a moment. Second one, what's u? What's du? Do you have to do anything fancy to make it work? No. So u equals x plus 1, du equals dx. This problem is integrating x dx plus du over u, or 1 over u du. See if you can finish. Well, sure. Well, I guess you could get 2, but what's a constant plus another constant? Still just a constant. So x squared over 2 plus the natural log of the absolute value of u plus a constant. I'm going to say x squared over 2 plus the natural log of the absolute value of x plus 1 plus c. We really should. We really should. And the next example will kind of show maybe why well, maybe not, I don't know. Yes, you should show the u substitution. Because technically our rule just says the integral of 1 over x dx is the natural log of the absolute value of x. It doesn't talk about 1 over anything else. Use the u substitution to make it fit that rule as is. Do you see how this is working? I guess you could have used synthetic division on this one, but I always use long division just because it will work for any sort of problem. The next one, synthetic division, wouldn't have worked. Question? Let's try this. Where is that one? Let's do the integral of 2x to the third plus 5x squared minus 10x plus 4 over x squared plus 4x dx. I think I'm going to kind of leave this mostly to you. What would the first step be? Why? What in the problem tells you that? Sure, and actually it's not even just one more, it's just any time it is greater than or even equal would also work. But if it's that case, do long division. You start it, I'll be a little bit behind you so you can check your work once you're done. And once you are done, though, see if you can finish off and integrate the thing. Hope you're getting 2x for your first division answer. 2x cubed over x squared? 2x? No, Caitlin? Yes. Okay. I think one of the toughest parts of long division is just keeping track of the signs. It is very easy to make a little sign mistake, which will throw things off. No, I don't think I can do anything else. I'm getting kind of an ugly looking remainder, but in some ways it's actually going to be really nice. I'm getting 2x minus 3 plus 2x plus 4 over x squared plus 4x after doing division. Maybe. Once you're there, split it into two problems. This one will be easy to deal with, and this one will require a u substitution. And it works out nicely. And see if it ended up being that. It was a pretty convenient remainder. You wouldn't be able to really deal with it otherwise. When we have our quiz Tuesday, I'm certain that one of the problems will require long division, and you just need to be on the lookout for any time that the degree of the numerator is greater than or equal to the degree of the denominator. And if you have that case, do long division. The point of that is that will let you rewrite it in another form, in a form that's easier to integrate. Part of it will be just straightforward integration, part will require a u substitution. And then 1, 2 more. Next thing we're going to take a look at. Definite integrals. You set this stuff for? What do you set with confidence? Definite integrals. We're going to do 2 of these. And then some trig stuff. The integral from 2 to 3 of x over x squared plus 1 dx, which means let's find the area under this curve, starting at 2, ending at 3. What should you probably do? U substitution. That's pretty much always our trick. What's u? X squared plus 1. What's du? 2x dx. I think you're going to make that work by sticking a 2 in and a 1/2 out. And I think we can make this 1/2 times the integral of du over u. What have I not yet dealt with? You got to change those. If I have u's in my problem, I need u values over there. How do we change those? Yeah, 2 is going to become, what is 2 going to become? 5. 2 squared plus 1, that's 5. And what does 3 become? That looks good. 3 squared plus 1, 10. Robbie.
Is it better if I ever just forget to change and take the two numbers integration, just use x at the end?
It's not handled formally correctly, though, because these must agree with the type of variable you have in there, so that would lose you a point. You'd probably get the same final answer, but it's not done in a formally proper way. Trey.
I just don't understand the switching from like the integral.
The point is, these are x values. X equals 2, x equals 3. It wouldn't make sense to have x values over here because there is no x in this problem anymore. There's now u's in the problem.
I don't understand how you apply it.
Oh, okay. That's an easy one. I have a formula over here that I created to convert x's into u's. When x equals 2, u is going to equal 2 squared plus 1, 5. When x equals 3, u is going to equal 3 squared plus 1, 10. I'm using that formula and applying it to those limits. That's where that's coming from. Now, what's the integral of du over u? The absolute value of u from 5 up to 10. I'm going to plug in 10 minus I'm going to plug in 5. Actually, absolute value of 10 is just 10. I don't need the bars there. I don't need the bars on the other one. I'm going to get the natural log of 10 minus the natural log of 5, 1/2 times that. However, when you have logs in your answer, I only want one natural log in the answer, not multiple ones. Is there any way Marissa, when you're subtracting logs, you divide the stuff inside. So this is really 1/2 times the natural log of 10/5, or 1/2 times the natural log of 2. Or, wait, say what again? Okay, first of all, we're not dividing natural logs. We're dividing the stuff inside the natural logs. So it's going to be the natural log of this number divided by this number, which is 2.
Why don't we have it use the x squared plus 1? Oh, wait, got it. You just plug in the original?
I haven't done anything with the... when we are doing definite integrals, that was the point of changing our limits into u values. We plug them in where the u is. We don't go back and resubstitute things in.
So we get rid of the original x squared plus
Yes,
1.
because we've already changed those things. There's one other way I could write the answer. Rohith?
Square root of natural log.
You're close.
Absolute value.
Not the square root of the natural log. The 1/2 goes inside there, becomes a 2 to the 1/2. It's just the square root of 2 inside the natural log. But not like the square root of the natural log thing. I have one more definite integral, and then we'll do some trig stuff.
You take either form, right?
But what?
You take either form.
Either form is fine, exactly. What I wouldn't take, though, is the one with the 10 and the 5. I want you to do better than that. The integral from 1 to 4 of x minus 2 over x plus 1 dx. How would I even think to start this one? Why would you say that?
Because the powers are equal.
Our rule is anytime the degree of the numerator is greater than or equal to the degree of the denominator, use division first. So ignore everything else going on here. I want to do x plus 1 divided into x minus 2. It's a quick, short division problem. Go do it. Maybe 1 minus 3 over x plus 1. I hope. My problem is the integral from 1 to 4 of 1 minus 3 over x plus 1 dx. Do you need a u substitution? Yes. But the problem is there's another part that doesn't require u substitution, right? You don't need that on the 1. So I'm going to split this into two problems. The integral from 1 to 4 of the constant 1 dx minus, why don't I just move that 3 out front, the integral from 1 to 4 of 1 over x plus 1 dx. I'm going to be fine with the first one. I'm just going to leave it as is for right now. With the second one, what's u? du. dx. And we're going to need to change those limits. 1 will become what? 2. And 4 will become? So we have problems here with two different sets of limits. I'm going to integrate 1 dx from 1 to 4 minus 3 times the integral from 2 to 5 of 1 over u du. Because that u substitution just applied to that 1/2 part of the problem. Go finish this off. Finish it off. And then we have trig integrals to deal with, and we'll be set for today. Actually, while you finish, I'm going to pass out the worksheet part of the homework. There's a little bit of book work. The rest is on a worksheet. We are definitely not done, though. You look very confused. What part am I confusing you by? Never mind. I'm misreading your face. What? Most of it's worksheet stuff. Yeah. So, what's the integral of 1? What has a derivative of 1? Just x. You can make it x. Sure, what has a derivative of 1 dx? X. Or, forget it, and you can think about its horizontal line at a height of 1, finding the area on 1 according to the rectangle as well. Okay, so I'm getting x evaluated from 1 up to 4 minus 3 times the natural log of the absolute value of u evaluated from 2 up to 5. That's 4 minus 1 minus 3 times ln of 5 minus ln of 2. Or we could say 3 minus 3 ln 5/2. Or make the 3 a power, or whatever. I'm just going to stop, though, with that one.
So it could be 3 minus ln to the 1.5 over 8.
Yes. Last thing that we need to deal with. Trig integrals. I'm going to look this up. Trig integrals. Sine, cosine, tangent, all those things. We already know 2 of them. They're really easy. The integral of the sine of x dx equals the positive or the negative cosine. Maybe. Try again. Negative. Negative cosine x plus a constant. And the integral of the cosine of x dx is the sine of x plus a constant. That is nothing new. I just kind of want those in here so all 6 rules are in one place. The integral of the tangent of x dx. We don't have a formula for this. That's the derivative, not the integral. Okay, how could we go about figuring this out? Let's try that. This is the integral of the sine of x over the cosine of x dx. And if you did that, let's try u substitution. What would u be? By the way, keeping in mind, du can never be in the denominator. So what's u? Let's try it. What's du? Negative sine x dx, which is basically what I have up top. I can make this work by sticking a negative inside and a negative outside. I can turn this into negative the integral of du over u. This is going to let me create the formula for the integral of the tangent of x. Okay, that's the negative of the natural log of the absolute value of u plus a constant, or the negative of the natural log of the absolute value of the cosine of x plus c. The integral of the tangent of x is the negative of the natural log of the absolute value of the cosine of x plus c. There's a lot of stuff there. There's an alternate form we can write this in. A negative out front could get moved where? To the power inside. I could say this is the natural log of the absolute value of the cosine of x to the negative 1 plus c.